All right, so for the example problem, let's just apply this. So I pretend I'm adding a new node here, except that I'm going to drop it later. For that reason, I just make the dotted node. And I added this one, m to m plus 1. This is called the root arc. I termed it 4, 5, or m to m plus 1. Nevertheless, you don't have many people conventionally call it the root arc. And there's a variable here which you can call, say, the x root variable or x45 variable. The remaining arcs, they are the regular arcs. You need also a bi value here, which is by convention 0. Okay? See, you don't see Node 5, nobody talks about that. So when you read your book, I don't think there's any mention of anything like this. But this is a good way of viewing the entire schema here. So if the requirement here is 0, since the only incoming arc is this new one, the variable here is always going to be 0. In flow conservation equations, that's what is imposed. There's only one incoming arc, so it has to be 0 because the external flow here is 0. Okay? For that reason, this will be a basic variable all the time, and we'll just keep that particular column in the basis all the time. So this is just a convenient way of handling all the operations of the network simplex methods. In our example, let's pick a tree here. For example, let's pick this tree with the root. And the basis matrix corresponding to this is going to have 1, 2, 3, 4 rows and 4 arcs. 1, 2, or variable x1, 2, 2, 3, 2, 4, and the root one, the root arc. Okay? And this has 1m minus 1. This one has 1m minus 1 positioned like this. This one has 1m minus 1 like that. The root node has 1 for position 4, minus 1 for position 5. Position 5 is dropped out, so it only has 1. In other words, it has the unit vector E sub m. Okay? So we've got our zeros here. That's my basis. And conveniently, it's a 4 by 4 basis rather than, 3 by 3. Because 3 by 3, anyway, this is the way people find it more convenient to work with. All right. So now what are we going to do with the basis matrices? Well, let's just recall the simplex method. We're going to simply use the simplex method as adapted to this new situation. we need to compute, or given a basis, we compute a number of things in a given simplex iteration. First, we compute the basic portion of the decision vector like that. xb is b inverse b. And then we also compute the w, the simplex multipliers, or the dual proposed solution, which is not feasible at all until you terminate at the end. W is defined by CB, B inverse. And then once we have W, we compute the reduced costs for the non-basic variables. But in general, it's going to be W, which is known now, minus C. Okay, that's the basic simplex operations. Once you've got all these things, you know who to enter, who to exit, and then you know also how to update the solution. Now, in our case, so on the right side, I'm going to write down what we do for this network simplex method. Instead of working with that, we work with b times xb equals b. Because if you pre-multiply both sides by b, that's what you get, bxb equals b. This is a system of equations that has as many unknowns in it as you have equations. It's a system that admits a unique solution. Why? Because B has linearly independent columns. Okay, that's why. All right, so we're going to work with this because this is easy to solve for minimum cost network flow problems. Because B is a tree structured or it's a matrix corresponding to a tree, and it's easy to solve. I'm going to demonstrate that using the example. For this one, again, rather than having B inverse, we simply post-multiply by B, and so that will give you a system of equations that requires you to solve for W, okay? W times V equals CB. Again, this is easy to solve for minimum cost network flow problems. And once you have this, of course, you can compute the other one easily. So let's do it using an example. The costs I have are 2. What is this? 4 minus 1, 6, 3, minus 5, and 7. All right, I gave you this example before. I hope the numbers are correctly printed. Anyway, we're going to use these numbers. And B1 is 4. B2 is 2, B4 is minus 5, and this one is, B3 is minus 1. That's what I have. So I've got 4 units of inflow here, 2 units here, 5 units coming out, 1 unit coming out. The red ones are external flows, okay? All right, so in the new situation, we added a new arc, which is this one, with an invisible node at the head of it, okay? And even though we never use B5, by convention, it's there, it's 0. And so we have a new variable here, which is always going to be 0, and which is always going to be basic, okay? So, let's pick a tree. Suppose we have the tree that I used before. What was it? Like this. Okay. All right. In this tree, the basis matrix is what is it? 2, 3, 2, 4, and the root. Okay, that's my basis matrix. So, solving for xp first. What do? We don't deal with the inverse. Rather, we simply solve this set of equations. If you write that, that gives you 1 minus 1, 0, 0, 0, 1, minus 1, 0, 0, 1, 0, minus 1, 0, 0, 0, 1, times xp, which consists of x12, x23, x24, and x root, equals 4, 2, minus 1, minus 5. That's what you have. That's the set of equations. Well, of course, if you write these equations down, what do you get? You get x12 equals 4. You got minus x12 plus x23 plus x24 equals 2. This one gives you minus x24, 23, minus x23 equals minus 1. What else? Minus x24 plus x root equals minus 5. Those are the set of equations you've got. And of course, because of the tree structure, you can see that you immediately have a solution. x12 equals 4. Once x12 is 4, well, x23 is 1. And once x12 and also x root is 0, we know that. Well, x root is always 0, so why is it always 0? Because you have to balance the flow here, okay? All right, so when x root is 0, x24 is definitely 5. So this gives you x24 value of 5. So I've got everything, I think. x12 is known, x23 is known, x24 is known. Do they add up to 2? They should. They should. Okay. All right. So this is easy to solve. I could do that also using the information here. So let me do it using the tree structure. That's the way we do it typically. Now, what you're doing here is the following when you look at this system. This system if you included the non-basic variables with their columns, the non-basic variables are 0 because you forced them to 0, okay? So you can just imagine in your head that you've got additional columns associated with non-basic variables and they are 0. So when the non-basic variables are 0, all you're doing is you're trying to satisfy the flow conservation equations using only the basic variables. That's all you're doing because all the non-basic variables are set equal to 0, okay? So let's just try to satisfy the flow conservation equations knowing the fact that all the non-basic variables are 0 and also the x root value is 0, okay? Now, if this is 0 and if you have 5 units coming out here, obviously you need to have 5 units coming in. So x24 is definitely 5. I'm using the tree here, okay? Now, over here, of course, we're going with the tip nodes of degree 1. This one has 1 unit coming out, so x23 has to be 1 unit coming in. And over here, I've got 5 plus 1 coming out, 6 coming out, 2 coming in already. So I need x12 value of 4, right? Which, of course, also balances this one. So it's easy. Of course, you have to draw the picture if you're doing it by hand. If you're not doing it by hand, if you're doing it by on the computer, then you need to take the 514 course to be able to do that efficiently using your digital equipment, okay? So certain data structures fit well with this, so you need to do that. But here, you're not learning first to be efficient. It's always more important to first understand what's going on and then become efficient, okay? So anyway, we're dealing with the main foundational elements here. So once you master these things, you can make them much more efficient later. So this is the solution. All the rest of the variables are 0, okay? All right, so that's for that. Next, the computation of W. That's my next topic. To do that, we need to solve the system defined by that, okay? W is the vector of dual variables. Now, you have a dual variable for each constraint. Since your constraints are associated with nodes, the dual variables are also associated with nodes. So remember that. You've got as many W's as you have nodes, okay? Times the B matrix, which in our case is 1, minus 1, 0, 0, 0, 1, minus 1, 0. The next one is 0, 1, 0, minus 1, and 0, 0, 0, 1. That's your WB. Equals CB. I have so little space left here, so I'm going to write it up here. CB has the costs associated with these columns. What are they? 2, 3, 2, 4, and root. So the cost of arc 1, 2 is 2. This is my first basic cost. My second basic cost is the one associated with 2, 3, which is minus 1. The next one is 2, 4, which is 4. The last one is 0. Did I mention that before? The root variable always has a cost of 0. If I did not mention it before, it's by convention always 0. So the cost of the root variable is 0. Okay? Why? Because the root variable will be 0 anyway, so it doesn't really matter what cost you assign to it. You might as well take it to be 0. Okay? All right. So you're setting these equations, and this will give you W1 minus W2 equals 2. Then W2 minus W3 equals minus 1. W2 minus W4 is equal to 4. And finally, W4 is equal to 0. Okay? That's your set of equations. All right, so we solve for this. What is the solution? I obviously get W4 equals 0 here. And then when W4 is 0, W2 is equal to 4. What is this, 4 or what? I can't read my handwriting. It has a little, yes, tag at the end. Okay, W2 is 4. And 4, so this will be what? 4 plus 1, right? W3 is 5. And what else? W2 is 4, so W1 is 2 plus 4, W1 is 6. You don't have to write all this down. I did it just to sort of relate to, linear systems of equations. But you can do it directly on your spanning tree. Okay? This is your spanning tree. So there's an imaginary node here, which you don't use. Now, W4, when you multiply the W vector with the last column, W times the column EM always picks up WM. Okay? And for that reason, if you look at the reduced cost for basic variables, let's denote the reduced cost associated with Xij by Rij. Now, this is equal to 0 for all basic ij, for all arcs ij in the tree under consideration, okay? Or those that are basic. Now, what is Rij? Rij is the W vector times the column associated with Xij, which is Aij, minus Cij. Okay? And in our case, this is taken to be 0, which means that this gives you the equation Waij equals Cij. It gives you that equation for basic ij's. Okay? All right, what is W times Aij? Well, Aij is this column with a +1 and a -1 in the ith and jth positions. So when you look at the W vector with W1, Wi, Wj, Wm, it will pick up Wi. So W times Aij minus Cij is simply equal to W, because of the +1 in ith position, minus Wj, because of the -1 in the jth position minus Cij. That's your reduced cost. And it gives you these equations. So that simply tells you, for the root node in particular, the reduced cost for our root is equal to 0, and it is W times EM minus the cost of root node. That's equal to 0. And W times EM simply picks up WM. C root is 0, so it simply gives you WM equals 0 all the time. Okay? For that reason, W4 is 0 directly. It's always the case. Now, if this is 0, let's put down the cost here. What was the cost here? This one was 2. These are the costs. Don't confuse them with the xij's. Minus 1 and 4. Okay? Now, what do you want in your set of equations? This simply tells you that Wi minus, so this is going to be equal to 0, which tells you that Wi minus Wj is equal to Cij. That's what you want. This is for arc ij in the tree. So the tail number, Wi, minus the head number, Wj, is equal to Cij. That's what you want. All right. The head number is available. So tail number minus that should give you 4, which means W2 is surely 4. If that guy is 4, 4 minus something here is equal to minus 1. How much is that something? 4 minus 5, right? 4 minus 5 is minus 1. What about here? This number minus 4 is equal to 2, so W1 is 6. Did I get the same solution? I hope. W1 is 6, W3 is 5, W2 is 4, W4 is 0. Yes. So you're progressing from tip nodes towards other nodes. Okay? As soon as you generate sufficient information, you are able to compute the rest of them. Okay. Next. Computing the reduced costs. Well, I already did that. Rij for non-basic variables. This is for non-basic variables. Rij for a non-basic arc is W times Aij minus Cij. That's the definition of it. The W times the column minus the cost, which gives you Wi minus Wj minus Cij. For non-basic ones, they don't have to be 0, okay? So whatever they come out to be. Now, W's are known now. So you are able to compute the reduced costs. Let's just compute them one at a time. R13 is going to be W1 minus W3 minus C13. W1 is 6 minus 5 minus C13. How much is C13? Minus 5. So how much is this? Minus 5 plus 5, so it's 6. It's positive, so you can enter this particular one if you wish. Okay? Positive reduced cost is eligible to be entered. This is a minimization problem. Let's just compute a few others. R32 will be W3 minus W2 minus C32. W3 is 5. W2 is 4. C32, 6. So how much is this? Minus 4. No, minus 5, right? Minus 5. Do not enter this one. What else? R34. That's going to be 5 minus 0 minus the cost of that particular one, 3. Which is 2. And then we also have R41. 0 minus 6 minus 7 minus 13. Don't enter it. So this tells you that you can enter either this one, 1, 3, or 3, 4. Since we typically choose the most positive one, let's just enter x13 or arc13. Okay? So computing reduced cost for non-basic arcs and selecting the entering variable. All right, I'm going to enter x13. Well, in the simplex method, you compute these ratios, etc., to identify the exiting variable. The purpose of that is to increase the entering variable as much as possible until some basic variable becomes 0. Okay, that was the main idea. We do the same thing here. We've got R3 here with these basic arcs. What was the solution I have? Whatever. These are the how much was this? X12 was in the current solution? 4. This one was 5. And this one was 1. This is the current basic solution. Now we decided to enter a new variable here, which was, what was it? 1, 3, yes. So I'm going to enter 1, 3 here. I'm going to increase it to the extent possible, because each unit increase here gives me 6 units of reduction in the objective value. Okay, reduced cost is 6, so it goes down by 6. So let's see how much we can increase. When you increase this guy, this is an input flow to number 3. So in the new solution, you still have to balance the equation at each node, which means that you have to decrease this one. That's the only one you can play with, because the other ones are 0, okay? The other ones that are incident at that. All right. Now, you again argue in the same way for node number 2. Node number 2 outflow is decreased by a certain amount, which means the inflow must change by the same amount. Okay? So this is also minus then. For this one, you're decreasing an outflow, you're increasing an outflow, so they cancel out each other, so everything is balanced. So if the old solution was balanced or feasible, then the new solution has to be feasible. Which means that if your increase is, say, delta, then your decrease is delta, your decrease is delta. So what is the largest increase you can have here? Well, the smaller of the negatively labeled ones. The smallest one is 1. So delta, in this case, will be at most 1, which forces this basic variable to go out or exit. Okay? That's the idea here. So my exiting variable is this one. In general, what do? We do a number of things. Insert the arc, the entering arc, into the current rooted tree. This creates a unique cycle. In the new subgraph, which includes the old tree plus the new entering arc. Okay? Why does it create a unique cycle? Because the old one did not have any cycle. When you inserted an arc, it creates a cycle. That's one of the properties of trees. Okay? In the cycle, assign a plus label to the entering arc and to all arcs in the cycle that have the same orientation as does the entering arc. That have the same orientation as does the entering arc. In other words, if I may have your attention for a moment, this arc has the counterclockwise orientation, this way. So if it is plus, this is a reverse arc, it has minus, it's minus. So in this case, there are no other arcs that have the same orientation. But if you did have other arcs in the same orientation as the entering one, that's what you would do. They would all receive plus. And the next bullet is essentially the same, except that in the cycle, assign minus label to all arcs that have the reverse orientation. As does the entering one. Okay? In this case, of course, both basic arcs in the cycle have reverse orientation, so they both received minus. Of the negatively marked arcs in the cycle, choose one that has a smallest flow value. In the current that has a smallest flow value in the current basic feasible solution. It is the one that exits. Okay? If you have ties, just pick one. In which case, of course, you will end up with a degenerate basic feasible solution in the next one, because simultaneously they will go down to 0, but only one of them will be basic. One of them will be non-basic, the other ones will be basic. Okay. All right, so in this example, we know that 2, 3 exits. Okay? There's only one. So we now update the solution. This one is increased by 1 unit. This one decreased by 1 unit becomes non-basic. This one is decreased by 1 unit, so it's 3 now. This one is not touched, so it stays the same, 5. This is, again, 0. So this is my new basic feasible solution. What is the basis? The basis is the one that corresponds to this rooted tree. So you can write it down if you wish. Okay? And let's compute again the W's. And for the W's, I need the cost information. What are the costs? So let me put down the costs in different colors somewhere. 2, -5, whatever, 4, and 0. These are the costs. Okay? So my W4 is 0. This minus that will be 4, so W2 is 4. And this minus that will give you, this minus 4 gives you 2, so W1 is 6. And 6 minus, what is this? It should give you 11. 11. Yeah, 6 minus 11 gives you -5. Okay? All right. Then compute reduce costs. R23, R32, R34, and R41. These are the ones I need to compute. R23. It will be 4 minus 11 minus the cost of that. R32, what is the cost of 23? 23 has a cost of -1. Yes, this is -1. The next one is 11 minus 4 minus the cost is 6. Okay? 3, 4. 11 minus 0 minus 3. 4, 1. I remember the cost is 7 for this one. And so 0 minus 6 minus 7, right? For some reason, I remember that one all the time. All right, so how much is this? 4 minus, this is plus, so 3 minus 11, that's -8. This one is 11 minus 10, which is +1.
-6?
-6.
The first one.
The first one.
Is it 6? 4?
5 minus.
Oh, 5. Okay, 5. Yeah. Okay, thank you. It doesn't matter. I don't enter it anyways. All right, 11 minus, yeah, this is 1. This one is 8. This one is -13. So enter x34 or arc34. And then when you enter that, let's just do that here. So I'm entering x34, which means I assign plus here. The cycle is here, and this receives minus. This one is also a minus. This one is plus, right? Of the negatively marked ones, this is the smallest one. So this one exits. update. We increased it by 3, so this is 3. This one increased by 3, so it's 4. This one decreased by 3, so it's 2. This one is also, well, it's gone now. Is this balanced? It should be. In other words, flow conservation must be satisfied. Of course, if you begin with a feasible basic solution, then everything will be feasible later on, unless you make a computational mistake. So it's good practice to check it from time to time to see if you're doing everything correctly. All right, so this is the situation. Compute the reduced costs now. W4 is 0. W2 is, I don't know, you need the cost information here again. This was 4. 3, 4 was, how much was that? 3. This one was minus 5. This one was 0. All right, so that will give you 4 here. This will be 3. And how much is this? Minus 8. No. Minus 2. Minus 2. Minus 2 minus 3 gives you minus 5. Okay. Etc. You got the picture. You know how to compute the rest of it. So just by doing this, you keep updating each time, improving the objective function. At least not you're not making it worse. In degenerate cases, you may sometimes do some stalling. When do you stop? Stop when Rij are all less than or equal to 0 for every non-basic ij. Okay? On Wednesday, I'm going to give you the extension of this to lower and upper bounded case. In that case, finding an initial basic feasible solution is also a burden. It's not a trivial one. So we need to set up a phase 1 problem to be able to generate a initial basic feasible solution. That'll be the end of it for this semester. Okay? See you on Wednesday.